So hello everyone. First time I use such a hand mic, so I hope it will work well and I don't try to eat it up. So welcome to the afternoon slots of this conference. My name is Dirk. I'm a principal solutions architect in Amazon Web Services. In my day job, I work with software companies on their multi-dimensional transformation.
And my name is Artem, and I'm a principal engineer with Amazon SQS SNS.
All right, let's kick it off. And we're talking about noisy neighbors, as you can see already. Probably nobody really likes noisy neighbors, I would agree. But maybe they can be less stressful if we find ways to isolate them. To make this all more tangible, let's also take this from an example scenario. So imagine you would want to build a multi-tenant solution that implements a rideshare service. So you are thinking big, and your customers are now large companies. Each of those companies are your tenants. And the employees of these large companies are actually the users of your rideshare service. This is obviously dramatically simplified here. So we only look at the ride booking service, but that's good enough for this talk. And we're particularly interested in this booking processing queue. There's obviously a ton of other downstream systems that will also contribute to the processing of everything. But what we are interested in here are those components. We have an API resource. Probably there's an API gateway-ish thing that manages that for us. We have a pre-processing resource that just does some sanity check, puts the booking request into the processing queue and immediately returns to the client to accept it. We have received your booking. Rest assured we are going to look after it. And then we wanted to decouple, and you probably too, wanted to decouple the pre-processing from the processing. For that we use the processing queue. And as we have learned in the keynote today, one of those aspects that we're looking after with queues is to reduce the temporal phase of coupling, which we're going to do here, but also to protect the downstream systems from peak loads. Now, when you want to start building such a thing, you would probably do it like most software companies do it, in the very simple way: create a multi-tenant queue for all of your tenants. Very simple. You don't have to do a lot when you onboard a new tenant. So that's great, as long as you have a balanced content of your queue here. So all tenants have an equal amount of messages, or at least there's nobody that stands out. But what if one of your tenants starts building up a huge backlog? So reasons for that are that one of your tenants, or the employees of one of your tenants, create a crazy amount of ride bookings. That's one reason. The other reason could be that processing of those bookings run into errors or take unexpectedly much time to do. And that makes you probably end up in such a scenario where we have tenant one that dominates the queue. And the other tenants will suffer from starvation, which is not good. So there are a number of mitigation patterns to address this. And patterns are a great means for architects anyway, right? And if those patterns even help you to mitigate pain points, that's even better. I said already, it's a great tool for architects to speak in patterns. And what is even more important, to understand patterns, and particularly the benefits and the trade-offs that you get from patterns, because you always need to pay with something for the benefits that you are getting. And this is why I always like to remind everybody that every architecture decision you take comes with a trade-off, or in other words, there's always something that sucks. And every architect should be aware of this, know the patterns and the trade-offs to pick the best choice on the table. All right, so let's look at some patterns. The first one is load shedding. You might think, why load shedding? Isn't that more of a general pattern that you can apply everywhere? Yes, you can, but you can also make use of it in such a situation. What does it mean? You just want to get rid of messages in a queue that have reached a certain age. And that might be really also useful in cases where your messages lose relevance quickly after a short amount of time. Let's go back to that example. If we look at the booking processing queue, let's assume we have an SLA of 5 minutes and then the end user should get the response for their booking request. And if after 5 minutes that message is still in here, we can also throw it away. It has no value anymore. So that's cool. Otherwise, in general, it is of course a quite drastic tool to follow. So you should really be aware that you might also do evil things with blindly throwing messages away, right? So it is in many cases, and also in this case, also more of a business decision than a technical decision when and where to throw messages away. Let's look at another also more general pattern, which is back pressure. One cool thing of queues is, everybody knows it, I don't have to explain it, that it can flatten peak loads. And there are situations where you have constantly fast producers and constantly slow consumers. This is in the lower case here, and that means over time the queues fill up. And we wouldn't rather want to keep message producers in general to slow down, but the ones that are responsible for sending those messages that belong to our noisy neighbor. And in this example here, we are in the fortunate situation that we also have end users that enter our system through the web. So we can actually also use our API gateway to throttle a tenant. Typically, in API gateway products, you have an API key that is assigned to a tenant, and you can assign a dynamic configuration, how many requests per time unit somebody can send. So that's cool. In other cases where you don't have an API entry point, you need to address the producers directly with producer flow control. And for that, you have to have access to your producers. And again, it is more of a business than of a tech decision. When to throttle and how to throttle. It is a pattern that can be used in combination with other patterns too. And now let's look at the other side of the spectrum. We started with a multi-tenant queue for everybody. The other side of the spectrum is one single tenant queue for each of your tenants. That looks super nice at the first glance and super easy and super straightforward. Nobody can harm any other tenant, so that's great. But if you look at the operational overhead, at the implementation overhead, and also at the cost penalty that might come along with it, it might not be the best solution because you have those tenants here that constantly need to poll your queues. And even if there is a tenant that doesn't produce a lot of messages, you still need to poll your queues, and that is a waste of resources. Artem and I just yesterday spoke with a customer who migrated away, or let's say refactored away from this situation because of the cost penalty. Oops, that was the wrong direction. So what we've looked at so far are the two extremes of the spectrum, one MTQ for N tenants and STQs for N tenants. Maybe we should look also at options somewhere more in the middle. And one thing we could look into is cell sharding. It follows the ideas of a cell-based architecture, and this is all about fault isolation and reducing the blast radius of when something goes wrong. And the idea here is that you just use dedicated queues for a subset of your tenants. You can use a sharding function like you would do with database sharding. It is, of course, a little bit simplified on this slide, but you get the idea, right? So as long as everything goes smooth, we don't need to look into that too much. But if now for the first cell, tenant 1 becomes a noisy neighbor, we see that only the other tenants in this cell are affected. In the other cells, no tenant is affected from that. So that's quite cool. You can isolate the blast radius, in this case, to 25% of your overall tenants. It comes, of course, with the respective overhead of implementing the onboarding and offboarding and making sure you choose a good and suitable sharding function for this. But other than that, it is no rocket science at all. All right, and now there are ways to mitigate noisy neighbor impact even more and without falling back into one single tenant queue as we saw before. And Artem is going to talk about it.
Thanks, Dirk. All right, so with shell sharding, we can reduce our blast radius to the number of cells. Essentially, with 4 cells, it's 25%. A noisy neighbor can only impact 25% of our customers, of our tenants, or with 100 cells, we would see 1% impact across the system. So the next strategy is to use shuffle sharding. With shuffle sharding, we still have multiple multi-tenant queues, but now we assign each tenant to several shards, 2, for example, in this diagram. In this example, we're in a steady state. No one is building a backlog. Our producers, they logically assign a pair of shards for every tenant using, for example, a hash function. And when publishing a message, the producer will pick one of the assigned shards that has the shallowest backlog. So how does it help? Let's say tenant 1 becomes a noisy neighbor, and now they start building a backlog in their both assigned shards. So when publishing a message for tenant 1, we're picking the shard with the least backlog. Doesn't really change anything. We're filling up both shards that belong to our tenant. But what happens, for example, for tenant 2 that has a partial intersect? They're assigned to shard 2 and shard 3. Shard 2 is impacted, but when we publish a message that belongs to tenant 2, our publisher realizes that shard 3 actually has no backlog, so it will direct all messages for tenant 2 into that shard. And tenant 2 now is not impacted anymore. Same goes for every other tenant. And now our impact is limited only to these tenants that are unlucky to share the same set of shards with the noisy neighbor. And this gives quite a significant benefit. So for example, if we have 100 shards and we assign every tenant to 5 shards, now the chance of having exactly the same 5 shards for 2 tenants is only 1 in 75 million. So our impact would be reduced to almost nothing when there is a noisy neighbor. It would be very unlikely to have 2 tenants sharing the same set of shards. But what are the trade-offs here? Well, first of all, every publisher needs to know the depth of the shard every time they publish a message. So for example, if I have 100 shards, it means I need to periodically poll the depth of every shard in every producer. So my polling rate is a multiplication of the number of shards times the number of producers. And it might not scale well as our capacity increases. And generally, it's not a nice property to have in a system where the more producers I have, the more work my system has to do in order to run. So what other strategies could we employ? Let's look at some hybrid strategies where we have a multi-tenant queue for most tenants, and we have a single tenant queue for selected tenants. So this is a typical approach used in, for example, software as a service solutions, where there are some special tenants that are paying extra to have a dedicated capacity. In that scenario, all messages that belong to such a tenant go into their own queue. This gives us all kinds of options what to do on the consumer side. We could, for example, have a dedicated consumer capacity just for that queue. This way, our dedicated tenant can never impact anyone else. If they generate a surge of traffic, they only impact themselves at worst. But we still don't really solve the problem for the rest of the tenants that are sharing the main queue. So how can we improve this? We could implement a dynamic queue dedication, dynamic overflow queue creation. This is how it would work. In the steady state, we have a single multi-tenant queue. All messages go into that queue. However, when producers publish a message, they look at the queue backlog, and if they realize that the queue is building a backlog, they scan the publish rate for every tenant according to their view of how many messages they're publishing per second. And if one tenant stands out, they dynamically create an overflow queue just for that one tenant, and they start directing all the messages into that queue. On the consumer side, again, having multiple queues, it gives us flexibility how to prioritize consuming from these queues. We could, for example, have a separate consumer fleet only reading from the multi-tenant main queue, and a separate consumer fleet only reading from the overflow queues. This adds complexity because, for example, producers, they need to tell the consumers that we've just created a new overflow queue just for that one tenant, so you need to start polling it. So this is a great mitigation. Now, when there is a noisy neighbor, they don't impact anyone at all. They get their own queue, no one is impacted. But it doesn't account for a scenario where the backlog in the queue is caused not by a tenant publishing a high volume of messages, but some kind of processing slowdown for messages that belong to a specific tenant. This could happen because, for example, our messages are links to some files, and some of these files for a specific tenant are large, or maybe processing messages for a specific tenant requires talking to a dependency that is slow or has little capacity. So how can we address this? The other approach is to flip it and detect noisy neighbors in the consumers. So how it would work? Again, we start with a steady state where everyone is publishing to the multi-tenant main queue. On the consumer side, we're monitoring how much time we're spending messages that belong to a specific tenant. If at some point we realize on the consumer side that we're falling behind the queue is starting to build a backlog, and we see that according to our local view, processing messages for a single tenant takes most of our capacity, most of our processing time. In that case, we could signal to the producers that, hey, tenant 2 is noisy. And once producers receive this signal, they will create an overflow queue for tenant 2. When this happens, again, we have the flexibility of how to load balance between the queues. We could, for example, first read from the multi-tenant queue, and only if it's empty, then we try to read from the overflow queue. Or we could implement all kinds of load balancing logic. So while this is a very effective mitigation strategy, it adds significant complexity. Consumers need to somehow tell producers that there is a noisy neighbor, which kind of defeats the whole purpose of, decoupling producers from consumer, making them independent. Now they need to have some shared state where they agree what is the list of overflow queues created dynamically for tenants, and where do we publish, where do we consume from. We also need some kind of cleanup logic for the time when a tenant stops being noisy. We don't want to be stuck in a state where tenant 2 has long stopped publishing messages, but our system is still having a dedicated queue for that tenant and keeps polling that empty queue for nothing. Over time, this could leak to an unbounded number of tenants. Such cleanup is also quite hard to implement, actually, because we can't simply delete the queue. We might risk deleting a queue just as the message lands here. So we need to have some kind of two-stage teardown process where first we tell the producer, stop publishing to this queue, I will still try to consume it. Then once we're sure that now for sure no one is publishing there, then we can tear down this queue and delete it, stop polling from it. Recently, in Amazon SQS, we have released a feature called Fair Queues that implements this pattern automatically. The way it works is that when publishing a message to a queue, producers can specify a tenant identifier. And under the hood, the system does the same, implements the same pattern we've just discussed. Because the system knows which messages are currently in flight, which messages have been received and not yet acknowledged, it knows how much time is spent processing messages for every tenant. So it can automatically detect that there is a noisy neighbor, the queue is building a backlog because of that noisy neighbor, and automatically create an overflow queue for that tenant. To the publishers, to the producers, and to the consumers, the whole system still looks like a single queue. But under the hood, the messages are now organized into multiple sub-queues. And when consumers try to receive a message, the system will prioritize returning messages from the multi-tenant main queue. It will only return messages from the overflow queue for any noisy neighbor once the main queue is empty, or once the processing time for that noisy neighbor drops to a level that is comparable to other tenants. This is a great mitigation, quite a simple one. Still has some trade-off. For example, we don't limit the amount of messages that the noisy neighbor can occupy on the consumer side, so they can still utilize all of the consumer capacity, which is generally a good thing. But now, if a new message is published into the main queue and all the consumers are busy processing messages from a noisy neighbor, the message for a regular tenant has to wait for a processing slot to become available on the consumers before it gets processed. So there is still some increase in the processing times, but now it's controlled and limited to the time it takes to process a message.
We have learned there's lots of patterns and lots of trade-offs. So again, the reminder for every architect to be fully aware of the trade-offs. Apparently, we could talk for ages about all this, but unfortunately, our time is up. So we just want to share a few actions and resources. If you want to learn more about SQS Fair Queues, you can look into the linked AWS blog on the left-hand side. If you're interested in building SaaS solutions and want to learn more about tenant isolation strategies, you can have a look into the white paper on the right-hand side. And other than that, thanks a lot for joining today. Please feel free to reach out to us on LinkedIn. And I guess time is up, but we will be around somewhere here for questions if you have any. Thanks a lot, and bye-bye.
Thank you.